Hello, and welcome to Late Physics, the channel where we explore the mysteries of the universe in a way that helps you relax, reflect, and maybe even drift off to sleep. Before we dive into today's topic, do me a favour, hit that like button and subscribe so you never miss an exploration into the wonders of space and science. And while you're at it, drop a comment letting me know where you're watching or listening from. Are you gazing up at the stars tonight? Or perhaps you're wrapped up in a cosy corner far from the vast reaches of space. Either way, you're joining us on an extraordinary journey, and I'd love to know how far this universe reaches, even here in our little corner of the world. Today, we're setting the stage for a profound adventure, a journey to the very beginning of everything we know. But before you imagine a loud explosion or something that feels more like a science fiction movie, let me ask. What do we really know about the beginning of the universe? How did everything we see, feel, and experience come into being? In the next few minutes, we'll explore the fascinating, complex, and sometimes mysterious story of the universe's birth, from its fiery origins to the subtle fluctuations that shaped its destiny. We're going to delve into the Big Bang, not as an explosion in space, but as a breathtaking expansion of space itself. You might even hear about theories and scientists you haven't encountered before, all piecing together the puzzle of our universe's earliest moments. So sit back, relax, and let's embark on this cosmic journey together as we try to answer the ultimate question. What actually happened at the beginning of the universe? What happened at the beginning of the universe? It's one of the most profound questions humans have ever asked. It's also one that has captivated minds for centuries, whether through the lens of philosophy, religion, or science. In today's video, we're going to explore the beginnings of everything we know, the moment or moments that shaped the cosmos. Now, we've all heard of the Big Bang, the most widely accepted explanation for how our universe began. It's a powerful story, one that suggests the universe exploded from an infinitely dense point, and from there, everything, space, time, matter, began to expand outward. The Big Bang model has guided our understanding for decades. But here's the thing, it's not the only theory out there. As we explore this topic, we're going to gently step beyond the familiar and consider some of the lesser-known ideas that scientists have proposed to answer this great question. These theories, some of them fascinating, challenge the boundaries of our understanding. Could the universe have always existed in some form, recycling itself in an endless cycle? Could there be multiple universes, each born from its own Big Bang? These ideas, though speculative, have expanded the limits of our imagination. But before we jump into the various theories, let's ask a simple yet profound question. What really happened before the Big Bang? Was there a before? Or did time itself, along with the universe, emerge together in a single, inescapable moment? This isn't just a theoretical question. It's one that challenges the very nature of time and existence. If we look back to when the universe began, did it come from something, or was it simply the first thing? What is so fascinating about the birth of the universe is that it's not just about the beginning of stars and galaxies, but the beginning of everything. How do we even begin to understand something that started with no space, no time, no matter? It's an incredibly humbling thought. As we reflect on this, we also realize just how little we truly know. We may have answers to some of the questions, but there are mysteries that remain tantalizingly out of reach. The universe itself, vast and ever-expanding, invites us to explore its secrets. From the discovery of cosmic radiation, which allows us to peer back in time to the moments after the Big Bang, to the ongoing work of scientists like Stephen Hawking, Roger Penrose, and many others, the search for answers is ongoing. And yet, the question lingers. Where did everything come from? Consider this. The earliest moments after the Big Bang, during a period known as the Planck era, happened in a fraction of a second, far too quickly for our current understanding of physics to fully explain. Even the most advanced theories of quantum mechanics and general relativity struggle to describe this era. The truth is there's so much we still don't know about the first few moments of the universe. Some theories suggest that the Big Bang wasn't the start of everything, but just the most recent event in an endless cycle. This idea, known as the cyclic universe model, proposes that the universe has gone through infinite phases of expansion and contraction, a process that stretches the limits of time and space as we understand them. Others, like the multiverse theory, challenge the very notion of a single beginning. Instead, they suggest that our universe is just one of many, each with its own distinct properties and origins. Could it be that our universe is only a small part of a much greater whole, a vast collection of separate but interconnected realms, each with its own laws and histories? These are big questions, some of them more philosophical than scientific, yet they shape the very frameworks we use to explore the universe. It's an exciting time in cosmology, because we're now on the verge of making discoveries that could answer these questions, or at least bring us closer to an understanding that's both mind-bending and deeply awe-inspiring. For example, the launch of new telescopes and satellites, such as the James Webb Space Telescope, promises to open windows into the earlier stages of the universe. With better tools to study the cosmic microwave background radiation, the afterglow of the Big Bang, scientists can probe even further back in time, pushing closer to the moment of creation. The quest to understand the universe's origins is no longer just a theoretical exercise. We are now equipped to gather evidence and test our ideas in ways that were previously unimaginable. As we delve into the depths of these mysteries, we begin to realize that the universe, in all its complexity, might not be a simple story with a clear-cut beginning and end. Instead, it could be a tale of transformation, rebirth, and cosmic evolution, one that unfolds in ways we are still learning to comprehend. The questions we're asking today may not have clear answers yet, but each step forward brings us closer to understanding the grand design of everything we see, hear, and feel. The universe invites us to ask big questions, to challenge the boundaries of human knowledge, and to imagine what lies beyond the stars. So, let's continue this journey. Let's keep asking these questions, no matter how complex or speculative they may seem. For in the search for answers, we may just find that the universe has much more to teach us than we ever imagined. The Big Bang model is one of the most famous concepts in cosmology, and for good reason. It offers us the most complete framework we have for understanding the beginning of the universe. But what exactly does it mean? At its core, the Big Bang theory tells us that the universe began as a singularity, a point where matter and energy were compressed to an infinitely small, hot, and dense state. Imagine every single particle, every speck of light, and all the space in the universe compressed into a volume smaller than a grain of sand. Then, around 13.8 billion years ago, this point began expanding at an extraordinary rate, growing rapidly into the vast, ever-expanding universe we see today. It's easy to think of the Big Bang as an explosion, but that's actually a misconception. The idea of an explosion suggests a violent event, like a bomb going off in a specific place, sending debris outward through space. But the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. Everything, including space, began expanding simultaneously. There wasn't a center to the universe where this explosion originated, because space itself was being stretched in all directions. This can be difficult to grasp, because our everyday experience doesn't give us much insight into the concept of space itself expanding. But think of it like this. If you were to imagine a balloon with dots drawn on it, the balloon's surface is like the fabric of space. As you inflate the balloon, the dots move away from each other, not because the dots are moving on the surface, but because the surface itself is expanding. That's the kind of expansion we're talking about with the Big Bang. Space itself stretched out, carrying everything along with it. The Big Bang model, as we understand it today, owes much to the work of a few brilliant scientists, many of whom were working independently in the early 20th century. One of the most influential figures was Georges Lemaître, a Belgian physicist and priest who first proposed the idea of an expanding universe in the 1920s. Lemaître was the first to suggest that the universe could have started as a primeval atom, a dense and hot state from which everything expanded. His work laid the groundwork for the Big Bang theory, although it wouldn't gain widespread acceptance until later. But Lemaitre wasn't the only one. Around the same time, Edwin Hubble, an American astronomer, made a groundbreaking discovery that would change everything we thought we knew about the universe. In the 1920s, Hubble observed that galaxies were moving away from us in all directions, and the farther away a galaxy was, the faster it appeared to be receding. This observation became known as Hubble's law, and it provided clear evidence that the universe was indeed expanding. The implications of Hubble's discovery were huge. It meant that the universe had to have been smaller and denser in the past, leading to the logical conclusion that the universe must have begun as a singularity. Another key figure was Alexander Friedmann, a Russian mathematician and physicist who developed independent models of an expanding universe. Friedmann's work used Einstein's equations of general relativity to show that the universe could be dynamic, meaning that it could expand or contract. This mathematical model of an expanding universe set the stage for much of what would later become the Big Bang theory. While Lemaitre was the first to suggest the idea, Friedmann's equations provided the mathematical framework for understanding how such an expansion could occur. We also have to acknowledge the contributions of Arthur Eddington, a British astronomer and physicist, whose work on the nature of the universe was ahead of its time. Eddington was one of the first to explore the possibility that the universe could have originated from a singularity. He also worked on understanding how light and gravity interact, and his ideas helped shape the modern view of how the universe's early moments might have unfolded. Though not as widely recognised as Lemaitre or Hubble, Eddington's contributions were crucial in guiding our understanding of the cosmos. While these scientists were instrumental in shaping the Big Bang model, there's another fascinating perspective that has emerged in more recent decades: the work of Alexander Vilenkin, a Russian-American theoretical physicist. Vilenkin is known for his contributions to the multiverse theory, which suggests that our universe is just one of many, each with its own set of physical laws. According to this theory, the Big Bang could have been just one event in an eternal cycle of creation and destruction, with new universes constantly being born. Vilenkin's ideas challenge the standard Big Bang model by proposing that the universe may not have had a singular definitive beginning at all. Instead, he suggests that the universe could have emerged from a quantum fluctuation, where the laws of physics as we know them break down, allowing for the birth of new universes from a quantum vacuum. This brings us to the concept of space-time geometry. What does it mean when we say that space itself is expanding? To understand this, we need to look at how space-time works. In simple terms, space-time is the fabric that makes up the universe. It combines space and time into one interconnected whole, and it's shaped by the presence of mass and energy. The more mass and energy in a region of space, the more it curves space-time, creating what we experience as gravity. The expansion of space itself is a stretching of this fabric, not just in one direction, but in all directions. As space expands, the distance between objects like galaxies just increases. However, this expansion doesn't occur within a pre-existing space. It creates space itself. This concept is one of the key insights provided by general relativity, which was developed by Albert Einstein in the early 20th century. General relativity tells us that gravity is not just a force between objects, but a result of the way mass and energy curve space-time. Now, let's talk about how this rapid expansion of space works in the early universe. The Big Bang model suggests that shortly after the universe began, it underwent a period of incredibly rapid expansion called inflation. Inflation is a theory that explains how the universe grew exponentially in the first few moments after the Big Bang. This theory, first proposed by Alan Guth in the 1980s, suggests that the universe expanded at a mind-boggling rate, far faster than the speed of light for a tiny fraction of a second. During this period, the universe went from being smaller than an atom to being vast and filled with energy and particles. Inflation helps to explain why the universe is so homogeneous and isotropic, meaning that it looks pretty much the same in all directions. Without inflation, the universe would have been much more uneven, with huge variations in temperature and density. But inflation smoothed things out, spreading energy and matter across the universe in a way that allowed stars and galaxies to eventually form. Inflation also ties into the idea of quantum effects in the early universe. During this rapid expansion, quantum fluctuations, tiny random variations in energy, were stretched out across space. These fluctuations would go on to influence the formation of large-scale structures in the universe, like galaxies and clusters of galaxies. The imprints of these fluctuations can still be seen today in the cosmic microwave background radiation, which provides a snapshot of the universe as it was just a few 100,000 years after the Big Bang. The Big Bang model, while incredibly successful, is not the final word on the universe's origins. There are still many unanswered questions. What caused inflation? Was there a cause before the Big Bang? Is the multiverse real? These are questions that continue to challenge scientists today, but the Big Bang model remains our best understanding of how the universe began, expanding from an incredibly hot, dense state into the vast, complex cosmos we see today. And as we continue to explore the universe, we may find that the answers we seek will expand not just our knowledge, but our understanding of what it means to exist in this vast and mysterious universe. When we look back at the earliest moments of the universe, we find ourselves entering a realm where the laws of classical physics seem to break down. It's a strange and unfamiliar world, where particles behave in ways that defy our everyday experience. To understand this, we have to venture into the heart of quantum mechanics, the branch of physics that governs the very small, things like atoms, subatomic particles, and the fabric of space-time itself. At the dawn of the universe, during the first few moments after the Big Bang, the forces that control our reality were not behaving in the way we usually understand them. The universe was so small and dense that quantum effects dominated its behaviour. To make sense of this, we need to delve into the ideas of two pivotal figures in the development of quantum theory, Niels Bohr and Werner Heisenberg. Niels Bohr, a Danish physicist, is often regarded as one of the fathers of quantum mechanics. He developed a theory called the Bohr model of the atom, which was revolutionary in its time. Before Bohr, scientists thought of atoms as miniature solar systems, with electrons orbiting the nucleus like planets around the sun. But Bohr introduced a radical idea. Electrons don't follow fixed orbits at all. Instead, they exist in discrete energy levels, and can only jump between these levels in certain ways. This was the first clue that, at microscopic scales, things don't behave the way we intuitively expect them to. But it was Werner Heisenberg, a German physicist, who took things even further with his uncertainty principle. Heisenberg's work revealed something that was deeply unsettling. At the quantum level, we can never know both the position and the velocity of a particle with absolute precision at the same time. The more precisely we know one of these values, the less precisely we can know the other. This principle shattered the classical idea that the universe was fully deterministic. Instead, it introduced the idea that there is an inherent uncertainty built into the very fabric of nature, a kind of fuzziness that governs the smallest scales of existence. These ideas are crucial for understanding the universe's early moments. In the hot, dense state of the universe right after the Big Bang, everything was governed by quantum mechanics, and space and time themselves were subject to quantum fluctuations, tiny random variations in energy that were stretched to cosmic scales. This brings us to one of the most intriguing concepts in modern physics: quantum foam. Quantum foam is the idea that, at the tiniest scales of space, on the order of the Planck length, which is about 10 to the minus 35 meters, space itself is not smooth, but rather it fluctuates wildly. This idea was proposed by John Wheeler, a pioneering physicist who worked on the development of quantum gravity. According to Wheeler, at the Planck scale, space-time is like a frothy, ever-changing sea of energy, with tiny fluctuations occurring constantly. These fluctuations aren't just theoretical. They're a part of the very structure of space-time. Imagine, if you will, a calm pond disturbed by the sudden appearance of ripples. In the early universe, these ripples were at the level of space-time itself, creating a chaotic environment where the usual rules of physics didn't apply. These quantum fluctuations played a crucial role in the formation of the universe's structure. As the universe expanded and cooled, these tiny fluctuations in energy were amplified, eventually leading to the formation of galaxies, stars, and clusters of galaxies. The process is subtle, but profound. The slight variations in density caused by quantum fluctuations became the seeds for the formation of all the cosmic structures we observe today. But the most fascinating part of all this is how quantum mechanics and gravity seem to intertwine, particularly when we consider the early universe. Gravity, the force that governs the large-scale structure of the universe, and quantum mechanics, which controls the smaller scales, have traditionally been thought of as separate realms of physics. But what if these two forces could merge? This idea is at the heart of a concept called quantum gravity, a theory that seeks to unify the laws of quantum mechanics with the theory of general relativity, which governs the force of gravity. One scientist who has contributed to this quest is Lee Smolin, a theoretical physicist who has explored the idea of a quantum theory of gravity. Smolin suggests that space and time themselves are not fixed and unchanging, but instead they emerge from the quantum interactions of matter and energy. His work challenges traditional views by proposing that space-time is not a passive backdrop for the universe, but rather an active participant in the process of cosmic evolution. If his ideas are correct, then gravity itself may be a quantum phenomenon, emerging from the very fabric of space-time at the smallest scales. In the early universe, before any stars or galaxies had formed, the laws of quantum mechanics were shaping the universe at a fundamental level. These quantum fluctuations, combined with the effects of gravity, created the seeds of structure that would later grow into the cosmic web of galaxies and clusters we see today. But to fully understand the early universe, we also need to look at the theory of cosmic inflation. Inflation is the idea that, in the first moments after the Big Bang, the universe expanded exponentially, growing by a factor of at least 100 trillion times in a fraction of a second. This rapid expansion stretched the quantum fluctuations across vast distances, imprinting them onto the fabric of the universe itself. These fluctuations, once microscopic, became the density variations that eventually led to the formation of galaxies and stars. Inflation helps to explain several important features of the universe, such as its large-scale uniformity and the distribution of galaxies. Without inflation, the universe would be much more uneven, with pockets of matter and energy clumping together in unpredictable ways. Inflation provides a mechanism to smooth out these irregularities, ensuring that the universe we observe today is relatively uniform, with small fluctuations that give rise to the structures we see around us. At the heart of inflation is the idea that the universe's earliest moments were driven by quantum effects. These effects, which are often unpredictable at the smallest scales, became the blueprint for the universe's large-scale structure. As the universe expanded and cooled, these quantum fluctuations were stretched out across vast distances, leaving an imprint on the fabric of the universe. Over time, these fluctuations grew, forming the galaxies and clusters of galaxies that we observe today. In this way, quantum mechanics played a pivotal role in shaping the universe, not just at the microscopic level, but on the larger scales as well. The quantum foam that existed in the early universe set the stage for the creation of everything we see around us. And as we continue to study the universe's early moments, we may uncover even deeper connections between quantum mechanics and the structure of the cosmos. The universe, it seems, is far stranger and more complex than we could ever have imagined. It's a place where uncertainty and fluctuation aren't just quirks of quantum theory. They are fundamental features of the cosmos itself. And as we look to the future, we'll continue to unravel these mysteries, revealing even more about the quantum nature of our universe and the forces that shaped it. Cosmic inflation is one of the most remarkable and important concepts in modern cosmology. Imagine, just moments after the Big Bang, the universe expanded exponentially, growing by an unimaginable amount in an incredibly short period. Faster than the speed of light, this rapid expansion, which lasted only a fraction of a second, set the stage for everything that came after. It's an idea that helps explain some of the most puzzling features of our universe, and it all started with a few key insights from scientists in the late 20th century. The concept of inflation was first proposed by Alan Guth in 1981, who suggested that in the earliest moments of the universe, space itself expanded incredibly fast, far faster than we can imagine. The universe grew by a huge factor in an infinitesimally short time, smoothing out any irregularities and setting the stage for the formation of galaxies, stars, and everything else we see today. This process of rapid expansion answers a number of fundamental questions in cosmology, such as why the universe appears to be so homogeneous and isotropic, meaning it looks similar in all directions. Without inflation, the universe would be filled with large temperature and density fluctuations, making the smooth and uniform cosmos we see today impossible. While Alan Guth is widely known for his role in developing the inflationary model, another physicist, Andrei Linde, played a crucial part in refining and extending this theory. Linde proposed the idea of chaotic inflation, which built on Guth's work by suggesting that inflation could happen in multiple regions of space, creating pocket universes. Each of these universes could have different properties, forming a multiverse of sorts. This idea of multiple universes, each evolving according to different laws of physics, was groundbreaking and has since become a key area of exploration in theoretical cosmology. But the concept of inflation didn't come out of nowhere. In fact, Andrei D. Sakharov saw a Russian physicist hinted at some of the principles behind inflation as far back as the 1960s. Sakharov is best known for his work on the theory of symmetry breaking, which describes how the fundamental forces of the universe came to behave differently after the Big Bang. He proposed that, in the early universe, there were phase transitions, like the transition of water from liquid to gas, that played a crucial role in shaping the fundamental forces. While his work didn't directly lead to the inflationary model, it set the stage for later ideas about how the early universe behaved, including the potential for rapid expansion. In the years following Guth's and Linde's work, other theorists began to explore alternative models that could explain the universe's early moments. Two such theorists, Paul Steinhardt and Neil Turok, proposed what is known as the ekpyrotic model of the universe. The ekpyrotic model presents an intriguing alternative to the standard inflationary theory. Instead of inflation being the cause of the Big Bang, Steinhardt and Turok suggested that the universe could have originated from the collision of two three-dimensional branes, short for membranes, which are multi-dimensional objects in the higher dimensional universe. According to this model, our universe is just one of many branes, and the collision between two of them could have sparked the Big Bang, providing a different explanation for the origin of the universe. Despite the alternative models, inflation remains the dominant theory because it provides a remarkably successful explanation for several key observations. For one, inflation explains the observed uniformity of the universe. During inflation, any initial irregularities in the universe would have been smoothed out, leading to the nearly identical temperature and density distribution that we observe in the cosmic microwave background radiation. Without inflation, we would expect to see much more pronounced variations in temperature across the sky, but instead, we find a very uniform background radiation, which supports the idea that inflation happened. One of the key aspects of inflation is how it ties into quantum mechanics. As the universe expanded, quantum fluctuations, tiny random variations in energy, were stretched to cosmic scales. These fluctuations became the seeds for the galaxies, stars, and clusters of galaxies that would form later. The pattern of these fluctuations is recorded in the cosmic microwave background radiation, which acts as a snapshot of the universe when it was just a few 100,000 years old. By studying the CMB, scientists can learn a great deal about the inflationary period and the quantum fluctuations that shaped the universe's structure. In recent years, there have been significant efforts to directly measure inflationary fluctuations, and one of the most important scientists leading the charge in this area is Max Tegmark. Tegmark has contributed to the understanding of the early universe through his work on cosmological data analysis, and by helping to develop new tools to study the faint imprints left by inflation in the CMB. His research has focused on using the latest observational data to provide more precise measurements of these fluctuations, which could help confirm or refine our understanding of inflation. Another scientist, Sean Carroll, has also made important contributions to the study of inflation, particularly in the context of how quantum mechanics and general relativity might be reconciled in an inflationary framework. Carroll's work has focused on understanding the quantum nature of the inflationary field and how it could explain the accelerated expansion of the universe. His research delves into the fundamental physics that governs the very early moments of the universe and seeks to answer some of the most profound questions about the origin of the cosmos. The study of inflation has far-reaching implications, not only for cosmology, but also for our understanding of the laws of physics. It brings together elements of quantum mechanics, general relativity, and particle physics, and challenges us to rethink our notions of space, time, and the very origins of the universe. Inflationary theory provides us with a model that fits beautifully with the observations we've made about the universe's large-scale structure, but it also leaves many questions unanswered. What caused inflation in the first place? How did the inflationary field emerge? And how does the multiverse concept fit into the larger picture of the universe's evolution? As we look toward the future, we can expect further advancements in observational techniques and theoretical models to help answer these questions. With the launch of powerful new telescopes, like the James Webb Space Telescope, scientists are poised to gather more data on the early universe, potentially allowing us to measure inflationary fluctuations with even greater precision. These efforts could help refine our understanding of inflation, or perhaps reveal new aspects of the universe's origin that we have yet to imagine. But for now, we can appreciate that inflation remains one of the most compelling ideas in cosmology. It provides a framework that ties together a vast array of observations, from the uniformity of the universe to the formation of galaxies. As we continue to explore the cosmos, we will no doubt uncover more details about this remarkable period in the universe's history, and perhaps one day we will discover the deeper forces that drove the universe to expand at such an extraordinary rate. So with inflation laying the foundation for the universe's evolution, we now transition to the next phase of cosmic history, the formation of matter itself. From the seeds of quantum fluctuations, the universe would begin to cool, allowing particles to form and eventually leading to the creation of stars, galaxies, and all the structures that make up the universe as we know it today. But that's a story for another time, one that takes us beyond the smooth, even universe shaped by inflation, and into a more chaotic, complex realm, where matter and energy begin to come together. The Planck era is a time in the universe's history that exists at the very edge of our understanding, so much so that we can only begin to imagine what it was like. It was the first fraction of a second after the Big Bang, a period characterized by temperatures and densities so extreme that the very fabric of space-time itself was in turmoil. This era, which lasted from 0 to approximately 10 to the minus 43 seconds after the Big Bang, is named after the Planck scale, the smallest measurable units of time, length, and energy in the universe. At this scale, the laws of physics as we know them break down. The universe was so small, dense, and hot that both quantum mechanics and general relativity, the two pillars of modern physics, would have had to work together to describe what was happening. But the truth is, we don't yet have a unified theory of quantum gravity that can describe the conditions of the Planck era. And that's one of the biggest puzzles in physics today, how to combine these two theories into a single framework that can explain everything from the smallest particles to the vast cosmos. The need for this unified theory becomes clear when we try to imagine what was happening during the Planck era. At this time, the universe was not just filled with energy, it was energy. There were no distinct particles or forces as we understand them today. Everything was compressed into a space so small and hot that our current theories of space and time lose their meaning. Instead of thinking about the universe as a collection of objects in a vacuum, we have to think of it as an intensely fluctuating quantum field, where all of the fundamental forces of nature were merged into one. One scientist who was deeply interested in these extreme early conditions was John Archibald Wheeler. Wheeler, one of the most influential physicists of the 20th century, proposed the idea of geons, gravitational entities that are formed by concentrated electromagnetic fields. Wheeler suggested that at the Planck scale, space-time itself might have been woven from such fields, and that the structure of the universe could have emerged from these quantum gravitational fluctuations. Though the concept of geons is not a direct description of the Planck era, it offered a glimpse into the kind of thinking that was necessary to understand how the universe began. Roger Penrose, another towering figure in modern physics, took a different approach in his work on the cosmological singularity. Penrose is best known for his contributions to our understanding of black holes and the nature of space and time. In the 1960s, he developed the concept of a singularity, a point where gravity is so strong that the laws of physics break down completely. His work showed that the universe could have begun from such a singularity, where the density and temperature were infinite, and all of space and time were compressed into an incredibly tiny point. But the difficulty with this idea is that it doesn't explain how the laws of physics themselves can be reconciled at such an extreme point. This is why the Planck era remains such a profound mystery. One of the most intriguing attempts to address the Planck era is the work of Lee Smolin, a theoretical physicist known for his research into quantum gravity. Smolin developed the theory of loop quantum gravity, which seeks to merge quantum mechanics with general relativity. In his view, space-time is not a smooth, continuous fabric, but is instead composed of discrete loops at the smallest scales. These loops represent the quantum structure of space-time itself. If Smolin's theory is correct, the universe might have begun as a quantum fluctuation, where the very structure of space and time itself was shaped by these loops. This would mean that the Planck era wasn't just a time of extreme heat and density. It was also a time when space-time was dynamic, fluctuating, and fundamentally quantum in nature. While loop quantum gravity offers a possible explanation for the Planck era, it is by no means the only theory on the table. Another approach, developed by physicist Edward Witten, proposes M-theory, a framework that unites several different string theories. String theory suggests that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings of energy. M-theory takes this further by proposing that these strings exist in higher dimensions, beyond the 3 dimensions of space and 1 dimension of time that we experience. According to M-theory, the early universe could have been governed by the interactions of these higher dimensional strings, and the Planck era could have been a time when these higher dimensions were manifest in the fabric of the universe. In addition to M-theory, there is the concept of ADS/CFT correspondence, proposed by theoretical physicist Juan Maldacena in the late 1990s. ADS/CFT is a mathematical relationship between 2 types of theories: anti-de Sitter, ADS, space, which describes a universe with a negative cosmological constant, and conformal field theory, CFT, which describes quantum fields at the boundary of space. Maldacena's idea is that these 2 seemingly unrelated theories could be equivalent, offering a new way to study quantum gravity. While ADS/CFT is still a developing area of research, it holds promise for understanding the quantum nature of space-time and could eventually provide insights into the conditions of the Planck era. The key takeaway here is that, although we don't yet have a complete theory of quantum gravity, there are several exciting and potentially transformative ideas that are helping us inch closer to an understanding of the Planck era. Whether it's through the loop quantum gravity approach of Lee Smolin, the string theory framework of M-theory, or the novel ADS/CFT correspondence, we're beginning to see how quantum mechanics and general relativity could be unified in a way that explains the extreme conditions of the Planck era. But even with these groundbreaking theories, the Planck era remains shrouded in mystery. We can't yet test these ideas with experiments because the conditions we need to observe are far beyond our current technological capabilities. However, as we continue to develop more sophisticated methods of observation, such as the study of gravitational waves and cosmic background radiation, we may eventually find ways to probe the early universe and test these theories in more concrete ways. The Planck era is the very beginning of everything we know. It's the foundation upon which all of space and time, matter and energy was built. But as we move forward in our quest for knowledge, we must acknowledge that the physics of this time is still beyond our reach. The early universe existed in a state that defies our current understanding of the laws of nature, and understanding this period will require breakthroughs in both theory and experiment. Yet, the search for answers in this realm offers the possibility of uncovering something profound, an understanding of how the universe itself came to be, not just in terms of matter and energy, but in terms of the very nature of space and time. As we continue to explore these mysteries, we move towards the next stage in the universe's evolution, the formation of the first particles. This is where the universe begins to cool, and matter starts to take shape, laying the groundwork for the stars, galaxies, and all the structures that will follow. But to understand how we got from the raw energy of the Planck era to the matter that makes up our world today, we need to look at how particles emerge from the chaos. That journey too is one of mystery and wonder, and it brings us closer to understanding the universe's ultimate story. In the earliest moments after the Big Bang, the universe was filled with an incredibly hot and dense soup of energy, where the building blocks of everything we know today were beginning to form. At first, the universe was so hot that atoms, and even the most basic particles, couldn't exist. But as the universe expanded and cooled, things began to settle into more familiar forms. This period, just moments after the Big Bang, saw the birth of the first elementary particles, quarks, leptons and photons, each of which would play a crucial role in the formation of everything that followed. Let's start with the quarks, the fundamental particles that make up protons and neutrons. In the very first moments, quarks were free to move around, interacting with each other in a way that is hard for us to imagine today. But they didn't stay free for long. As the universe cooled, quarks began to combine, forming protons and neutrons. This was a key moment, because protons and neutrons are the building blocks of atomic nuclei, and the formation of these particles set the stage for the creation of atoms themselves. The idea that quarks are the fundamental building blocks of protons and neutrons was first proposed by Murray Gell-Mann in the 1960s, and Gell-Mann's work revolutionized our understanding of particle physics by introducing the quark model, which suggests that protons, neutrons and other hadrons are made up of smaller particles called quarks. According to Gell-Mann's theory, quarks come in 6 types, or flavors: up, down, charm, strange, top and bottom. These flavors combine in different ways to form the particles that make up matter. For example, a proton is made up of 2 up quarks and 1 down quark, while a neutron is made up of 2 down quarks and 1 up quark. However, quarks don't just appear out of nowhere. They interact with other particles through fundamental forces, which is where the electroweak theory comes in. The electroweak theory, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1960s, combines 2 of the 4 fundamental forces of nature, the electromagnetic force and the weak nuclear force. These forces, which were once thought to be separate, were shown to be different aspects of the same underlying force. This theory was groundbreaking because it provided a unified explanation for how particles interact at the most fundamental level. It also explained how particles like quarks and electrons could interact with each other, and gave us a deeper understanding of the forces at play in the early universe. But the formation of particles wasn't just about the quarks and the forces between them. it was also about symmetry breaking, the idea that the laws of physics could change in different conditions, especially as the universe cooled. Roger Penrose, a British physicist, explored the role of symmetry breaking in the early universe. Penrose's ideas on cosmological singularities, points in space-time where gravity becomes infinitely strong, helped us understand how particles might have emerged from quantum fluctuations. Penrose's work on symmetry breaking suggests that in the very early universe, as it cooled, the forces and particles that governed the universe underwent a series of phase transitions. These transitions helped shape the structure of the universe and the fundamental particles that make it up. Another physicist who contributed to our understanding of particle interactions is David Bohm. Bohm, known for his interpretation of quantum theory, proposed a more holistic view of quantum mechanics. He believed that the strange, seemingly random behavior of particles could be understood in terms of an underlying hidden order. According to Bohm, particles don't just move randomly, they follow a deeper, more connected set of principles. His ideas about quantum theory and the potential hidden layers of reality could provide new insights into how particles interact, even in the chaotic environment of the early universe. As the universe continued to cool, the formation of elementary particles became more stable. Quarks began to combine into protons and neutrons, while electrons and other leptons floated around. Photons, particles of light, also began to play a significant role in the evolution of the universe. In the early universe, photons were constantly interacting with the charged particles that filled space. But as the universe cooled, these interactions began to slow down, and photons were able to travel freely through space for the first time. This allowed light to spread out across the universe, creating the cosmic microwave background radiation that we observe today. The formation of these particles was an essential step in the creation of atoms, but there was still much more to happen. Once quarks had combined to form protons and neutrons, and electrons were present, the next major step was the formation of atomic nuclei. In the first few minutes of the universe's existence, nuclear reactions began to occur. Protons and neutrons collided, forming the first atomic nuclei, primarily hydrogen and helium, with trace amounts of lithium. This process, known as Big Bang nucleosynthesis, created the building blocks for the atoms that would eventually form stars and galaxies. But while the birth of particles and atoms was happening, the universe was still a very different place from the one we know today. It was a hot, dense environment filled with energy and radiation. This chaotic, energetic state gradually gave way to a more stable, structured universe. As the universe expanded and cooled, the particles that had formed in the early moments of the Big Bang would eventually come together to form the stars, galaxies, and larger structures that make up the universe we observe today. The birth of particles was just the beginning. These tiny, fundamental particles are the building blocks of everything in the universe, from the stars in the sky to the atoms that make up your body. Their interactions, governed by the forces of nature, set the stage for the more complex phenomena that would follow. And as the universe cooled and matter began to take shape, it was these interactions that would give rise to the first atoms and eventually the first stars. As we move forward in the story of the universe, we come to a critical point, when matter begins to cool enough to form the first atoms. But to understand how that happens, we first need to explore how the universe's cooling process allowed for the creation of the stable atomic structures that would give rise to the galaxies and stars we see today. From the birth of elementary particles to the formation of atoms, the universe was on the verge of becoming a more familiar place. A place where the building blocks of matter could begin to take shape and form the universe we know and love. As the universe continued to expand and cool, it reached a critical point where the temperature and energy levels were low enough for matter to start coming together. This cooling allowed the first atoms to form, primarily hydrogen and helium, the most abundant elements in the universe. This was the beginning of a process called recombination, which occurred about 380,000 years after the Big Bang. Recombination is the moment when electrons combined with protons and neutrons to form neutral atoms, marking a major turning point in the universe's evolution. In the early universe, atoms couldn't form because the temperatures were so high that the energy of individual photons was enough to ionize atoms, stripping electrons away from protons. This state, where the universe was full of free electrons and protons, is called the plasma era. The constant scattering of photons off free electrons meant that light couldn't travel freely, making the universe opaque. But as the universe expanded and cooled, temperatures dropped enough for electrons to bind with protons, creating neutral hydrogen atoms. This allowed photons to travel freely for the first time, and these photons make up what we now observe as the cosmic microwave background radiation. Robert Dicke, an American astrophysicist, played a significant role in understanding this period. He was instrumental in the theoretical understanding of the cosmic microwave background, CMB, proposing in the 1960s that the residual radiation left over from the Big Bang would still be detectable. Dicke's work predicted that this radiation would be faint but ubiquitous, and it was only later, in the 1960s, that Arno Penzias and Robert Wilson accidentally discovered this radiation, confirming Dicke's predictions. Jim Peebles, another key figure in cosmology, helped refine our understanding of the thermodynamics of the early universe. His work, alongside others, focused on how the universe cooled after the Big Bang, and how that cooling allowed atoms to form. Peebles was one of the first to use the newly discovered CMB to understand the conditions of the early universe. His insights helped solidify the Big Bang model as the most accurate explanation for the origins of the universe. Alongside these developments, Michael Turner, a leading cosmologist, made significant contributions to our understanding of cosmological inflation and the large-scale structure of the universe. Turner's research on the early universe and structure formation showed how the slight fluctuations that existed in the plasma during the era of recombination became the seeds for the formation of galaxies. He helped establish the theoretical framework for how matter and energy evolved from a uniform early state into the complex structures we see today. Turner's work connected the dots between inflation, which expanded the universe rapidly in its earliest moments, and the growth of cosmic structures that formed later. The era of recombination was a pivotal moment, not just because it allowed photons to travel freely, but because it set the stage for the universe to become transparent. After this period, light could travel through space without being scattered, allowing it to travel vast distances and eventually reach us. This moment, which we can observe today through the CMB, is one of the most important clues about the early universe. Alan Guth and P.J.E. Peebles were also central to the development of theories explaining how recombination led to the formation of the CMB. Guth, as we've discussed, is famous for his theory of cosmic inflation, which proposed that the universe expanded exponentially in the first fractions of a second. This rapid expansion stretched quantum fluctuations to cosmic scales, setting the foundation for the temperature and density variations we see in the CMB. Peebles, who contributed greatly to our understanding of cosmological structure and dark matter, helped build on this by applying statistical mechanics and thermodynamics to explain how the CMB formed. In the aftermath of recombination, the universe began its transformation into a more familiar state. As photons could travel freely, the universe's light was no longer trapped within a hot, dense plasma, and the CMB became a relic of that early time. It is one of the most direct pieces of evidence we have about the universe's birth. This radiation has been travelling through space ever since, cooling and stretching as the universe expanded. Today, it provides us with a snapshot of the universe when it was just a few 100,000 years old. But the story doesn't stop there. After recombination, the universe wasn't yet the complex, star-filled space we see today. The next big step in the universe's evolution came with the emergence of structure formation. This concept, championed by scientists like Neil Turok, refers to the way matter began to cluster together, You're forming the seeds for galaxies, stars, and clusters of galaxies. Turok's work on structure formation focused on how slight density fluctuations, imprinted in the universe by quantum fluctuations during inflation, grew over time due to the influence of gravity. These fluctuations were tiny, but they were enough to cause matter to accumulate in certain regions, eventually leading to the formation of galaxies and stars. This process is still ongoing, with galaxies continuing to cluster together, forming the large-scale structure of the universe that we observe today. Dark matter played a crucial role in this process. Though we can't directly observe dark matter, we know it must exist because of its gravitational effects on visible matter. As matter in the early universe began to cool and condense, dark matter served as a kind of scaffolding, helping to pull normal matter into clumps. Over time, these clumps formed galaxies, and later larger structures like galaxy clusters. The clustering of dark matter, in combination with ordinary matter, was the driving force behind the formation of the cosmic structures that make up the universe. The CMB is often referred to as the afterglow of the Big Bang, and its study has provided invaluable insights into the universe's early conditions. By analysing the tiny fluctuations in the CMB, scientists can learn about the density, composition, and structure of the universe at the time of recombination. These fluctuations tell us a great deal about the processes that led to the formation of the first stars and galaxies, as well as the overall evolution of the universe. As we continue to study the CMB and the universe's early history, we gain more insight into how matter began to cool and form the structures that we observe today. The universe's transition from a hot, dense plasma to a cooler, more stable state was a critical moment in its evolution. It was during this time that the universe went from a featureless soup of energy to a structured space filled with matter. This period also set the stage for the formation of the first atoms, as well as the cosmic structures that would grow to include stars, planets, and galaxies. The universe was still in its infancy, but it was starting to take shape. The cooling of matter, the formation of hydrogen and helium atoms, and the separation of photons from matter all marked the beginning of a new chapter in the story of the universe. The cosmic microwave background is more than just a faint relic of the past. It is a cosmic fingerprint that offers a glimpse into the universe's birth, and every study of it helps us piece together the story of our cosmic origins. As we move forward, we will continue to learn from the CMB, uncovering even more about the early moments of the universe and how it evolved into the complex structured cosmos we see today. The cosmic microwave background radiation, or CMB, is often referred to as the afterglow of creation. It is the faint, persistent radiation left over from the Big Bang, and it serves as a snapshot of the universe when it was just about 300,000 years old, long before the formation of stars and galaxies. This radiation has been travelling across space ever since, providing us with a direct record of the universe's early conditions. Yes, the CMB is one of the most crucial pieces of evidence we have for understanding the universe's infancy, offering a rich field for cosmological study and a glimpse into the very nature of the cosmos. The discovery of the CMB was entirely accidental. In 1965, two scientists, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, trying to detect radio signals from the Milky Way. However, no matter how much they adjusted their equipment, they kept picking up a persistent, uniform signal that seemed to come from every direction in the sky. At first, they thought it was some kind of interference, but after thorough investigation, they realized they were detecting something much more significant, the faint echo of the Big Bang itself. Penzias and Wilson's accidental discovery of the CMB was a monumental breakthrough, providing strong evidence for the Big Bang model of the universe. In recognition of their work, they were awarded the Nobel Prize in Physics in 1978. This discovery opened the door for a deeper understanding of the early universe and its evolution, laying the foundation for decades of subsequent research. But the story of the CMB doesn't stop there. In the early 1990s, another breakthrough occurred with the launch of the Cosmic Background Explorer (COBE) satellite. The COBE mission was designed to measure the CMB with unprecedented precision, and its results were nothing short of transformative. Two of the key scientists involved in analysing COBE's data were George Smoot and John Mather. Their work led to the discovery of tiny fluctuations, or anisotropies, in the CMB that provide critical insights into the structure of the early universe. Anisotropies refer to small, irregular variations in the temperature and density of the CMB across different parts of the sky. These variations are incredibly subtle, but they contain an immense amount of information. They tell us how the universe was shaped in its earliest moments, providing clues about its overall geometry, its expansion rate, and the distribution of matter. In fact, these tiny fluctuations are the seeds from which all the structure of the universe, including galaxies, stars, and planets, ultimately formed. Smoot and Mather's work on the CMB earned them the Nobel Prize in 2000, yet as their findings confirmed much of what cosmologists had long suspected, that the universe, in its earlier stages, was much more complex than a uniform soup of matter and radiation. The CMB is not just a snapshot of the early universe, it also provides critical information about the forces that shaped it. One of the key features of the CMB is its uniformity. Almost every point in the sky has nearly the same temperature, with only minute fluctuations. This uniformity was one of the key puzzles that needed to be explained. How could the universe, which was so small and hot at the time of the Big Bang, evolve to be so uniform? The answer came with the development of the theory of cosmic inflation. Cosmic inflation, as we discussed earlier, is the idea that the universe underwent a period of rapid expansion in the first fractions of a second after the Big Bang. This inflationary period stretched out any irregularities in the universe, smoothing them out and creating the uniformity we see in the CMB. At the same time, tiny quantum fluctuations, random variations in energy, were stretched to cosmic scales, leaving behind the slight anisotropies we observe today. These fluctuations were the seeds of all the structure in the universe, and understanding them has been one of the central goals of modern cosmology. As we continue to study the CMB, we uncover more details about the conditions of the early universe. One of the scientists who has made significant contributions to the area is Catherine Freese, a theoretical physicist known for her work on dark matter and its potential connections to the early universe. Freese's research has explored how dark matter, which makes up most of the mass in the universe, may have played a role in the formation of structure in the early universe. She has proposed that dark matter could have influenced the development of the fluctuations seen in the CMB, shaping the way galaxies and clusters of galaxies formed. While dark matter remains invisible and undetectable by direct means, its gravitational effects are essential for understanding how the universe evolved from the hot, dense state of the early universe to the complex web of galaxies we see today. Another area of research that has been tied to the study of the CMB is the idea of primordial gravitational waves. These are ripples in spacetime itself that were created by inflation and could have left a distinct signature in the CMB. The detection of primordial gravitational waves would provide direct evidence for inflation and could help answer some of the most fundamental questions about the universe's earliest moments. Though these waves have not yet been detected, they remain a key target for future experiments, such as those being conducted by the BICEP experiment in Antarctica and the Planck satellite, which continues to study the CMB in greater detail. The study of the CMB has been one of the most fruitful areas of research in cosmology over the past few decades, helping to confirm many of the predictions of the Big Bang Theory and providing new insights into the nature of the universe. But the CMB is not just a relic of the past. It is also a bridge to understanding the future of the universe. By studying the tiny fluctuations in the CMB, scientists can learn about the properties of dark matter and dark energy, the mysterious substances that dominate the universe's composition. These studies could eventually lead to a deeper understanding of the universe's fate, whether it will continue to expand forever or eventually collapse in a big crunch. As we move beyond the study of the CMB, we begin to transition to another critical phase in the universe's evolution, the formation of galaxies and stars. The fluctuations in the CMB provided the initial conditions for this process, but it was the gravitational collapse of matter, aided by the presence of dark matter, that led to the formation of the first galaxies. These galaxies would go on to form the first stars, which in turn would give rise to all the elements necessary for life as we know it. Understanding the CMB helps us trace the path from the simplest, earliest universe to the complex, structured cosmos we now inhabit. The CMB is not just a relic of the past, it is a message from the universe itself, a record of the moment when light first travelled freely through space, allowing us to peer back into the universe's infancy. As we continue to study it, we uncover more about the origins of the universe, the forces that shaped it, and the mysteries that remain. It is a testament to the power of observation, the beauty of scientific inquiry, and the endless curiosity that drives our quest to understand the cosmos. After the era of recombination, when the universe had cooled enough for atoms to form and light could travel freely, a new phase began, the birth of the first stars and galaxies. These early stars, known as population 3 stars, were the first sources of light in the universe, and their formation marked the beginning of cosmic history as we know it. Unlike the stars we see today, which are made of a mix of elements formed in earlier stars, population 3 stars were composed almost entirely of hydrogen and helium, the simplest elements created during the Big Bang. The process of star formation in the early universe was a complex and mysterious one. One scientist whose work has provided key insights into this process is Volker Bromm. His research on early star formation theories shows that the first stars formed within dense clouds of hydrogen and helium gas that collapsed under their own gravity. As these clouds contracted, the gas heated up, and the pressure increased. Eventually, the temperature became high enough for nuclear fusion to occur, and the first stars were born. These stars were likely much larger and hotter than the ones we see today, and their intense radiation played a crucial role in shaping the universe's early evolution. However, the formation of stars was just the beginning. These early stars also contributed to the creation of galaxies, the fundamental building blocks of the universe's structure. The formation of galaxies was tightly linked to the creation of molecular clouds, vast, cold regions of space where matter could gather and form new stars. Ralph Pudritz, a Canadian astrophysicist, contributed greatly to our understanding of the role of molecular clouds in galaxy formation. He showed that these clouds were essential for the birth of stars, as they provided the raw material from which stars could form. These molecular clouds, made up mostly of hydrogen gas, became denser and colder as they collapsed under gravity, allowing stars to form in clumps. Over time, these stars began to group together, forming the first galaxies. These early galaxies were small and irregular, vastly different from the large spiral galaxies like our Milky Way. However, they laid the foundation for the larger structures that would eventually emerge as the universe expanded and cooled. Joseph Silk, a prominent figure in cosmology, also made significant contributions to our understanding of the early universe's structure and star formation. Silk's theories focused on how the first galaxies formed in the aftermath of the Big Bang. He proposed that the earliest galaxies were shaped by the interplay between dark matter and ordinary matter, with dark matter providing the gravitational scaffolding that helped pull gas and stars together. Silk's work has been instrumental in understanding the formation of galaxies, especially in relation to the growth of structure in the universe. One of the most fascinating phenomena to occur after the first stars were born was the process of reionization. Before the first stars lit up the universe, the gas in the cosmos was completely ionized, meaning it was broken down into free electrons and protons with no neutral atoms. But when the first stars began to shine, their intense ultraviolet radiation ionized the surrounding hydrogen gas, turning it back into a plasma. This process, known as reionization, marked a major shift in the state of the universe. Alan Bird, a cosmologist, proposed a detailed theory of reionization that helped explain how this transition occurred. Bird's research suggested that the first stars played a central role in ionizing the hydrogen gas, creating regions of space where photons could travel freely much as they do today. This process of reionization cleared the way for light to travel across vast distances, allowing us to observe the universe as we do now. It also marked the point at which the universe became transparent to radiation, leading to the formation of the large-scale cosmic structure we see today. The birth of the first stars and galaxies, and the process of reionization, played a critical role in shaping the universe's evolution. As stars formed and light began to spread across the cosmos, as galaxies began to cluster together, forming the intricate web-like structure of the universe. These galaxies and their stars acted as the building blocks for the complex structures we see today. The formation of the first galaxies was a pivotal moment in cosmic history. It set in motion the processes that would eventually lead to the rich tapestry of stars, galaxies, and other structures that fill the universe. But the birth of galaxies also laid the groundwork for the more complex phenomena that followed. As galaxies began to merge and collide, new stars formed, and matter began to group together in larger and more structured ways. Over billions of years, this process continued, with galaxies growing larger and more complex, eventually leading to the formation of clusters and superclusters of galaxies. In addition to the gravitational forces at work during galaxy formation, the presence of dark matter was a crucial factor. Dark matter, which makes up roughly 25% of the universe's mass, provided the gravitational pull necessary to gather normal matter and form the structures we observe today. While we still don't know exactly what dark matter is made of, we do know that it played a key role in shaping the universe's early structure. Its gravitational influence helped to create the cosmic web of galaxies, stars, and clusters that define the large-scale structure of the universe. As the universe continued to evolve, the formation of galaxies gave rise to the stars and planetary systems that would eventually host life. The birth of stars is closely tied to the creation of heavier elements, such as carbon, oxygen, gas, and nitrogen, which were forged in the cores of these stars. These elements are the building blocks for planets, including Earth, and for the life that has since emerged in the universe. Understanding how stars and galaxies formed is not only crucial for understanding the universe's past, but also for understanding the conditions necessary for life to exist. The transition from a universe filled with primordial gas to one filled with stars and galaxies was a gradual process, driven by the forces of gravity, radiation, and the fundamental laws of physics. It was a time when the universe began to cool and stabilize, allowing the first structures to take shape. The birth of stars and galaxies marked the beginning of the universe's journey from a hot, uniform state to the complex and diverse cosmos we see today. As the first stars ignited and galaxies formed, they also set the stage for the larger-scale structure of the universe. Over billions of years, these galaxies would continue to evolve, merging and growing in size, and ultimately forming the clusters and superclusters that define the cosmic landscape. From these early building blocks, the universe would continue to expand and evolve, giving rise to the complex structures and phenomena that we observe today. The process of galaxy formation, with the birth of stars and the role of dark matter in shaping the cosmic structure, offers us a window into the universe's past. It is a fascinating story of how the universe went from a simple, hot and dense state to the richly complex and structured universe we observe today. And as we continue to study these processes, we gain a deeper understanding of not just the universe's history, but also the forces that continue to shape it. The idea that the universe is expanding might sound almost too grand to grasp, but it's been one of the most important discoveries in the history of cosmology. It all began with Edwin Hubble, whose work in the early 20th century laid the foundation for our understanding of the universe's growth. Hubble observed something remarkable. Galaxies, Instead of being stationary or moving randomly, were all receding from us. In fact, the farther a galaxy was, the faster it appeared to be moving away. This observation led to what is now known as Hubble's law, which states that the velocity at which a galaxy moves away from us is directly proportional to its distance. This phenomenon of galaxies moving away from us was a direct consequence of the redshift, the stretching of light as it travels through the expanding universe. When light from distant galaxies reaches us, the wavelengths of that light are stretched out, shifting them towards the red end of the spectrum. The more distant a galaxy is, the greater the redshift, meaning the light is stretched even more. This is a key piece of evidence showing that the universe is not static, but expanding. Hubble's discovery was groundbreaking, but it didn't provide answers to all the questions about the nature of the universe's expansion. For instance, while we know that galaxies are moving away from us, why are they doing so, and what will the universe's ultimate fate be? In the late 20th century, these questions became even more pressing as more evidence about the expansion emerged. One of the most significant contributions came from Vera Rubin, an astronomer whose work on galaxy rotation curves helped us understand more about the structure of the universe and the forces driving its expansion. Rubin's research focused on the motion of stars within galaxies, particularly their rotational speeds. She found something unexpected. The stars at the outer edges of galaxies were moving much faster than they should have been, based on the visible matter in those galaxies. This discrepancy suggested that there was more mass in galaxies than we could see, an invisible substance, which came to be known as dark matter. Dark matter doesn't emit light or energy, but its gravitational effects are noticeable, particularly in galaxy rotation. Rubin's work helped reveal that dark matter plays a significant role in the structure of galaxies, and its distribution also has a profound impact on the universe's expansion. But while dark matter was helping to shape galaxies, another significant discovery would emerge in the form of observations of distant supernovae. In the 1990s, astronomers studying these exploding stars made a surprising discovery. Not only was the universe expanding, but the rate of expansion was accelerating. This was unexpected, as scientists had assumed gravity would eventually slow the expansion down. Instead, they found that the universe's expansion was speeding up, suggesting that some mysterious force was pushing galaxies apart. The discovery of the accelerated expansion of the universe earned Saul Perlmutter, Brian P. Schmidt, and Adam Riess the Nobel Prize in Physics in 2012. Their work, based on observations of distant supernovae, provided the crucial evidence that the expansion of the universe is not slowing down, as we might have expected, but instead accelerating. This discovery introduced the concept of dark energy, a mysterious force that is counteracting gravity and driving the universe's expansion. Alongside these major discoveries, Alexei Filipenko, an observational cosmologist, made significant contributions to our understanding of supernovae. He played a key role in developing methods for using supernovae as cosmic distance markers, allowing astronomers to measure vast distances across the universe with greater accuracy. Filipenko's work provided essential data for understanding the rate of expansion of the universe, which has been critical in the study of dark energy and the universe's ultimate fate. The discovery of dark energy and the accelerating expansion of the universe raised new questions about the universe's future. If the expansion continues to accelerate, will galaxies continue to move away from each other until they are unreachable? Or could some other force intervene, eventually slowing the expansion and possibly even reversing it, leading to a contraction? These questions have profound implications for our understanding of the universe's ultimate fate. The study of dark energy and the rate of expansion continues to be one of the most active areas of research in cosmology today. One of the key aspects of studying the universe's expansion is understanding the large-scale structure of the cosmos. The universe is not uniformly distributed, with galaxies scattered randomly throughout space. Instead, galaxies tend to cluster together in vast networks, forming a cosmic web of filaments and voids. The study of this large-scale structure helps cosmologists understand how galaxies and clusters of galaxies formed, and how gravity and dark matter have influenced the distribution of matter over billions of years. The expansion of the universe and the study of its large-scale structure are closely connected. As the universe expands, galaxies move farther apart, but the gravitational forces within galaxies and clusters can still overcome the expansion, keeping galaxies bound together in groups. This means that while the overall universe is expanding, the galaxies within clusters remain in close proximity. Over time, galaxies will continue to interact with one another, merging and forming larger galaxies. This process of galaxy mergers, along with the influence of dark matter, plays a key role in shaping the universe's structure. The study of redshift, galaxy rotation curves, dark matter, and dark energy all provide valuable insights into the universe's expansion. These discoveries have revolutionized our understanding of the cosmos, and the next step is to explore the formation of light elements through Big Bang nucleosynthesis. As the universe continued to expand and cool, hydrogen, helium, and trace amounts of other elements formed in the first few minutes after the Big Bang. These light elements would go on to form the building blocks of stars, galaxies, and eventually planets. The process of Big Bang nucleosynthesis provides a crucial piece of the puzzle when it comes to understanding the origins of matter in the universe. The expansion of the universe is one of the most fundamental aspects of our cosmos. From Hubble's discovery of redshift to the study of dark energy, these findings have changed the way we think about the universe. But there are still many questions left to answer. How will the universe end? What role does dark energy play in the expansion, and what will the future hold for galaxies and their stars? The answers to these questions will likely shape our understanding of the universe's ultimate fate. As we explore the formation of light elements and Big Bang nucleosynthesis, we move closer to understanding how matter first came together in the early universe, setting the stage for the stars, our galaxies, and planets that followed. The universe is an ever-expanding mystery, and each discovery brings us one step closer to understanding its vast and awe-inspiring story. In the first few minutes after the Big Bang, the universe underwent an incredibly dramatic process that laid the foundation for everything that would follow. This was the era of Big Bang nucleosynthesis, a period in the universe's early history when the first light elements were formed. Hydrogen, helium, and traces of lithium were synthesized in the hot, dense environment that existed just after the Big Bang, and these elements would go on to form the building blocks of stars, galaxies, and eventually planets. The process of nuclear synthesis began when the universe had cooled enough for nuclear reactions to take place. The first element to form was hydrogen, in the form of a single proton. This hydrogen was followed by helium, formed when protons combined with neutrons in nuclear reactions. Helium-4, the most common form of helium, was the primary product of these reactions, but small amounts of other light elements like deuterium, a heavier isotope of hydrogen, and lithium also formed in lesser quantities. The understanding of this early period in the universe was shaped by the groundbreaking work of several scientists. Ralph Alpher and Robert Herman were two key figures who worked on the theory of Big Bang nucleosynthesis. In the late 1940s, Alpher and Herman, along with George Gamow, developed a model that predicted the relative abundances of the light elements that would form in the first few minutes after the Big Bang. According to their calculations, hydrogen would be by far the most abundant element, followed by helium and trace amounts of deuterium and lithium. Their work provided the first concrete predictions of the element ratios in the early universe, setting the stage for future discoveries. George Gamow, a Russian-American physicist, was another pioneer in this area of research. He is often remembered for his key early work in cosmological theory, particularly for developing a model that predicted the light element distribution in the universe. Gamow was one of the first to suggest that the elements we observe in the universe were formed during the Big Bang, and his work on nuclear synthesis in the early universe laid the groundwork for much of our current understanding. His predictions were later confirmed by observations, and making his contributions fundamental to the development of the Big Bang theory. In addition to Alpha, Hermann and Gamow, another influential figure in understanding the distribution of elements in the early universe was James Peebles. Peebles, a Canadian-American astrophysicist, contributed significantly to our understanding of cosmological structure and the formation of elements in the early universe. He expanded on the ideas of Alpha, Hermann and Gamow, providing a more detailed understanding of how the early universe's conditions allowed for the synthesis of light elements. Peebles also made important contributions to the study of the cosmic microwave background CMB radiation, which offers a snapshot of the universe just after the Big Bang and provides critical evidence for the Big Bang nucleosynthesis model. The synthesis of these light elements in the first few minutes after the Big Bang is important for several reasons. First, it provides us with insight into the conditions of the early universe. The specific ratios of hydrogen, helium, and other light elements that we observe today are consistent with the predictions of Big Bang nucleosynthesis, making this a strong piece of evidence for the Big Bang theory. Second, these light elements set the stage for the formation of stars. Stars are essentially giant nuclear reactors, fusing lighter elements like hydrogen and helium to create heavier elements, which in turn allows for the formation of planets, moons, and other structures. The hydrogen and helium created in the first few minutes after the Big Bang provided the fuel for the first stars, and their fusion reactions would give rise to the heavier elements needed to form planets and life. While Big Bang nucleosynthesis explains the formation of the light elements, it also highlights some of the challenges we face in understanding the origins of the universe. One of the key questions that arises is why the universe produced the specific mix of elements that we observe today. The abundance of hydrogen, for example, is overwhelmingly greater than that of helium or lithium. This is in part due to the fact that hydrogen is the simplest element, consisting of just one proton and one electron, making it much easier to form in the early universe. Helium, on the other hand, required a more complex nuclear process, and so only a small amount of it formed relative to hydrogen. The exact ratios of these elements tell us a great deal about the conditions in the early universe, but we are still working to understand why the universe evolved in this particular way. As we move from the synthesis of light elements to the formation of more complex structures, we begin to explore how these elements were used to form the first stars. The process of star formation is closely tied to the evolution of galaxies and other cosmic structures, and it all begins with the raw materials created in the first few minutes after the Big Bang. The hydrogen and helium atoms formed during Big Bang nucleosynthesis were the basic building blocks for the first stars, which were born from the collapsing gas clouds of the early universe. But before we move on to star formation, let's consider the broader picture of how these elements laid the groundwork for the universe we see today. The hydrogen and helium produced in the Big Bang are not just the building blocks for stars, they are the foundation for all of the matter in the universe. From the formation of stars and galaxies to the creation of planets and life, everything in the universe is made of the elements created during the first moments of the Big Bang. As the universe cooled and matter began to stabilize, it created the perfect conditions for the formation of structures. The synthesis of light elements during Big Bang nucleosynthesis set the stage for this process. Hydrogen and helium served as the raw material for the first stars, and as those stars formed and began to burn, they produced heavier elements through nuclear fusion. These heavier elements, like carbon, oxygen, and nitrogen, would eventually form the building blocks for planets, moons, and life itself. It's hard to overstate just how fundamental this early synthesis of light elements is to the development of everything that came after. Yet, as we delve deeper into our understanding of the early universe, we encounter challenges to the Big Bang model. For one, there are still many unanswered questions about the specific details of Big Bang nucleosynthesis. While the general predictions about the relative abundances of hydrogen, helium, and lithium are well supported by observations, The exact processes that led to these abundances are still being studied. Moreover, the origin of the dark matter and dark energy that dominate the universe remains a major mystery. These substances are invisible to us, yet they exert profound gravitational effects on the visible universe, shaping the formation of galaxies and other structures. As we look to the future, the challenge is to continue refining our understanding of the universe's origins, not just through studying light elements, but through investigating the deeper mysteries of dark matter and dark energy. But no matter how much we uncover, the Big Bang nucleosynthesis model remains a cornerstone of cosmology, offering us a glimpse into the universe's infancy and the foundation of the matter that makes up everything we know. From the synthesis of light elements to the formation of galaxies, we see how the earliest moments of the universe laid the groundwork for the stars, planets, and life itself. And as we continue to study these processes, as we move ever closer to understanding the true origins of the cosmos and the forces that shaped its evolution, the universe's early history is still unfolding before us, and each new discovery brings us closer to uncovering the secrets of its creation. Despite all we've uncovered about the universe's origins, there remain deep mysteries that continue to elude our understanding, particularly when it comes to the very earliest moments. The Planck era, the first fraction of a second after the Big Bang, remains a profound enigma. The extreme conditions of density and temperature during this time push the limits of our current theories, and it's an era where even the most advanced laws of physics seem to break down. What happened before the Big Bang? How did the universe come to be in the first place? These are the fundamental questions that remain unanswered. The challenge with understanding the Planck era lies in the fact that we currently have no unified theory of quantum gravity. We rely on two major pillars of physics: quantum mechanics, which governs the very small, and general relativity, which governs the very large. However, these two theories don't work well together in extreme conditions like those found in the Planck era. In this realm, where both the fabric of space-time and the smallest quantum particles were in play, a new theory is required, one that unites quantum mechanics and gravity to describe the earliest moments of the universe. While we have some promising ideas, a complete theory of quantum gravity is still just out of reach. This limitation has prompted scientists to explore alternative theories that stretch our imaginations and offer new ways of thinking about the universe's origins. One such idea comes from Lee Smolin, who proposed the concept of cosmological natural selection. Smolin's theory suggests that the Big Bang is not a singular event, but part of a cyclical process, where universes are born, evolve, and eventually die, through a process known as the Big Crunch. According to Smolin's idea, each new universe formed from a Big Bang could have slightly different physical constants, and through a process akin to natural selection, universes with properties that allow for more stable conditions, such as the creation of stars and galaxies, would survive longer, while others would collapse back into singularities. In essence, the Big Bang would be part of an ongoing cyclical process, with each universe potentially contributing to the creation of the next. Roger Penrose, another influential figure in cosmology, took a similar but different approach with his conformal cyclic cosmology model. Penrose's theory suggests that the universe undergoes an infinite series of cycles, where each cycle begins with a Big Bang and ends with a Big Crunch, followed by a new Big Bang. However, in Penrose's model, each cycle is not just a repetition of the previous one. Instead, the universe's geometry evolves in such a way that each new cycle is different from the last. The idea that the universe could go through infinite cycles challenges our traditional view of time and space, proposing a more dynamic and ever-changing cosmos. Penrose's theory is still in its early stages, but it offers a compelling alternative to the standard Big Bang model, suggesting that the universe's history may be far more complex than a single linear timeline. Then there is the idea of the multiverse, proposed by Max Tegmark and others. The multiverse theory suggests that our universe is just one of many in a vast and possibly infinite collection of universes. According to Tegmark, There could be countless other universes, each with its own set of physical laws and constants. These universes could be born from their own big bangs, and they may be completely disconnected from ours, making them impossible to detect. The multiverse hypothesis arises from the mathematical framework of quantum mechanics and cosmology, and it suggests that our universe may not be unique at all. Instead, it may be just one of an endless number of universes, each with its own distinct properties. The implications of this idea are profound, as they challenge the very notion of our universe as a special or unique place in the cosmos. The multiverse concept, while fascinating, raises questions that are difficult to answer. If there are other universes, can we ever detect them? Can we ever know if they exist, or are they forever beyond our reach? These are some of the most intriguing and difficult questions in modern cosmology. While the idea of a multiverse may seem like science fiction to some, it is grounded in serious theoretical research, and it has opened up new ways of thinking about the universe and its origins. Despite these exciting ideas, it's clear that we're still far from a full understanding of the universe's beginnings. Even with the advanced theories proposed by scientists like Smolin, Penrose and Tegmark, the question of what happened at the very start remains elusive. Current physics has provided us with a detailed understanding of the universe's evolution, from the moment of the Big Bang onward. But when it comes to the Planck era and what came before, we're left with more questions than answers. The next breakthrough in cosmology may come when we finally develop a theory of quantum gravity, but for now the mysteries of the earliest moments of the universe remain tantalizingly out of reach. As we stand on the brink of new discoveries, it's important to remember that the search for answers is ongoing. Theoretical physicists and cosmologists are constantly developing new ideas and refining old ones. In the coming years, new technologies and observations will allow us to peer even further into the universe's past. For example, next-generation telescopes and particle accelerators may offer new ways of testing these theories, potentially providing the clues needed to solve some of the most profound questions in science. One exciting area of exploration is the study of gravitational waves, ripples in space-time caused by massive events like black hole mergers, and possibly even the Big Bang itself. These waves carry information about the early universe, and as detection methods improve, we may be able to use them to probe the universe's origins in ways that were previously unimaginable. Gravitational wave astronomy, in its early stages, could be the key to unlocking some of the mysteries of the Planck era and the very beginning of the universe. As we continue to explore the origins of the universe, we are likely to encounter new challenges and mysteries that push the boundaries of our understanding. The future of cosmology is bright with potential, and with every discovery we come one step closer to answering the most profound questions about our existence. What happened before the Big Bang? Was there even a before? How did the universe begin, and what will its ultimate fate be? These are the questions that drive us forward, shaping the next chapter in the story of the cosmos. For now, we continue our search, knowing that with each new discovery, we come closer to unraveling the mysteries that have intrigued humanity for millennia. The universe, it seems, still has much to teach us. As we continue to unravel the mysteries of the cosmos, it's clear that we're living in an exciting time for cosmological discovery. The future of cosmology promises to be filled with groundbreaking advancements, thanks to new tools, emerging theories, and innovative technologies. The James Webb Space Telescope, set to revolutionize our understanding of the universe, is at the forefront of these advancements. With its unparalleled ability to peer into the distant reaches of space, the James Webb Space Telescope is designed to observe the universe in infrared wavelengths, allowing us to see the very first stars and galaxies formed after the Big Bang. This will provide us with insights into the formation of the early universe and help answer some of the most pressing questions in cosmology, from the birth of galaxies to the nature of dark matter. The power of the James Webb Space Telescope lies not only in its advanced technology, but in the precision it will bring to cosmological measurements. Its instruments will enable us to detect faint signals from objects millions and even billions of light years away, providing a clearer picture of how the universe evolved. Observations from Webb are expected to shed light on how the first stars ignited, how galaxies merged, and even how black holes formed in the early universe. With the help of this powerful tool, we're on the verge of answering questions that have remained elusive for centuries. Alongside advancements in observational technology, work in theoretical physics continues to offer new perspectives on the universe's fundamental nature, whereas scientists like Sarah Burrell and Luca Amendola are making significant contributions to our understanding of dark energy and dark matter, two of the most mysterious forces driving the expansion of the universe. Dark matter, which makes up around 25% of the universe's mass, interacts with gravity but doesn't emit light or energy, making it invisible to traditional telescopes. Dark energy, on the other hand, is believed to be responsible for the accelerated expansion of the universe. Both of these elusive forces remain largely mysterious, but the work of Burrell and Amendola, among others, could reshape our understanding of how the universe is structured and how it has evolved. Burrell's research, for instance, explores how the distribution of dark matter in the universe affects the formation of galaxies and galaxy clusters. So, by better understanding how dark matter interacts with visible matter, she's contributing to our broader understanding of the universe's large-scale structure. Meanwhile, Luca Amendola is delving into dark energy and how it influences the accelerated expansion of the universe. His work focuses on how different models of dark energy can affect the rate of expansion, which in turn could tell us more about the ultimate fate of the cosmos. As important as these advancements in observational and theoretical cosmology are, we're also entering an era where artificial intelligence, AI, is playing an increasingly vital role in analysing the vast amounts of data being collected. The universe is vast and incredibly complex, and the sheer volume of information gathered from space telescopes, particle accelerators, and other scientific instruments is overwhelming. In response, researchers are turning to AI to help process and analyse this data more efficiently. AI has the potential to identify patterns and make predictions that humans may overlook. In cosmology, AI is being used to analyse data from the James Webb Space Telescope, detect exoplanets, and study the distribution of galaxies across the universe. One of the most promising uses of AI is in the search for dark matter. By analysing the gravitational effects of dark matter on visible galaxies, AI can help scientists understand its distribution and behaviour. AI's ability to sift through massive data sets could provide new insights into the cosmic phenomena that shape our universe, including the distribution of galaxies and the formation of cosmic structures. Perhaps one of the most exciting possibilities AI brings to cosmology is in the development of new theories. With a vast amount of data available, AI algorithms could potentially uncover new patterns in the way galaxies form or how cosmic forces interact. This could lead to the formulation of new hypotheses and perhaps even the discovery of phenomena that have previously gone undetected. Looking ahead, the future of cosmology is rich with potential for new discoveries that could challenge and expand our understanding of the universe. As we study the earliest moments of the cosmos with tools like the James Webb Space Telescope, we will gain insight into the birth of galaxies and stars, providing us with a clearer picture of how the universe evolved. These discoveries could shed light on some of the most fundamental questions about the universe's origins, from the nature of dark matter to the forces that drive its expansion. At the same time, the ongoing work of physicists and cosmologists will likely lead to breakthroughs in our understanding of quantum gravity, the theory that seeks to unite the laws of quantum mechanics and general relativity. A theory of quantum gravity would provide the answers to some of the most profound questions in cosmology, such as what happened during the Planck era, the first moments after the Big Bang. As our theoretical models become more refined, and as observational tools like the James Webb Space Telescope and other next-generation instruments come online, we may finally be able to answer these fundamental questions. While the future of cosmology is full of promise, it is important to remember that the process of discovery is ongoing. With each new technological breakthrough, each new observation, and each new theory, we get one step closer to understanding the true nature of the universe. The questions that have intrigued humanity for centuries, such as the origins of the cosmos, the nature of dark matter and dark energy, and the ultimate fate of the universe, remain at the forefront of scientific inquiry. The journey of discovery is far from over, and every new piece of the puzzle brings us closer to a more complete understanding of the universe. As we continue to push the boundaries of our knowledge, we will undoubtedly encounter new mysteries that will drive the next generation of scientists and explorers. Just as the discovery of the Big Bang, as dark matter and dark energy reshaped our understanding of the cosmos, future breakthroughs will continue to challenge and expand our perceptions of the universe. As we look forward to the exciting discoveries on the horizon, it is clear that cosmology will continue to evolve. From the tools we use to observe the universe to the theories we develop to explain it, the future of cosmology holds endless possibilities. The mysteries of the cosmos are vast and complex, but with each new discovery, we get one step closer to unlocking the secrets of the universe's birth, its evolution, and its ultimate fate. The journey of exploration continues, and the future of cosmology promises to be as awe-inspiring as the universe itself. As we bring our journey through the early universe to a close, we can take a moment to reflect on how far our understanding has come. The Big Bang Theory has guided us through the unfolding of the cosmos, from its fiery origins to the formation of the first particles, stars, and galaxies. This journey has not only provided answers but also raised new questions, ones that continue to challenge our comprehension of the universe and our place within it. We've seen how, just moments after the Big Bang, the universe began to expand, creating the vast expanse of space that we see today. From the first moments of cosmic inflation to the formation of light elements in the early universe, each step has revealed more about how the universe was shaped. We've learned about the birth of the first stars, the intricate dance of dark matter, and the still mysterious force of dark energy that drives the accelerated expansion of the universe. However, despite the tremendous strides we've made, we must acknowledge that many mysteries remain. The Planck era, the very beginning of time itself, still eludes us. We don't yet have a complete theory of quantum gravity to explain the extreme conditions at the birth of the universe. The origins of dark matter and dark energy remain profound puzzles, and there are still open questions about the true nature of the multiverse and the ultimate fate of the cosmos. These unresolved mysteries remind us that even in our best attempts to understand the universe, we are only scratching the surface. But it is through this uncertainty that science thrives. Every discovery brings us closer to the answers we seek, and with each breakthrough, as we learn more about the very fabric of reality. Just as the discovery of cosmic radiation confirmed the Big Bang Theory and our understanding of the early universe, future discoveries, perhaps through advancements like the James Webb Space Telescope or new theories in quantum gravity, will continue to illuminate the darkest corners of space and time. The ongoing nature of discovery is what makes cosmology so captivating. It encourages us to look up at the stars and wonder about the forces that have shaped them, and it invites us to contemplate the vastness of the universe and our role within it. The pursuit of knowledge is never-ending, and with each question answered, new questions emerge, urging us to dive deeper into the mysteries of existence. In the grand scheme of things, our place in the universe is but a fleeting moment, yet our ability to reflect on it, to ask questions and to seek understanding is a testament to the power of human curiosity. The universe, in all its vastness, is a reminder of how much there is to explore and how little we truly know. Yet, that very mystery is what makes it so beautiful. As we move forward, let's continue to embrace the unknown, knowing that each step we take in the pursuit of knowledge brings us closer to uncovering the origins of the universe and the forces that govern it. The journey of discovery is not just about the answers we find, but about the questions that continue to spark our imagination and fuel our drive to explore the cosmos. The universe is vast, and we are only just beginning to understand the story it has to tell. In the quiet of the night, when you gaze at the stars, remember that you are not just looking at distant lights. You are looking back in time to moments long past, to the birth of the universe itself. That wonder, that curiosity about the cosmos, will continue to guide us as we journey ever deeper into the mysteries of space. And who knows what we'll discover next? The universe has its secrets, but as long as we keep asking the questions, the answers will eventually unfold.